Hey guys, sorry if you already watched my other screencast on projectile motion, but I looked at it, I thought, yeah, I think I emphasized some things that didn't need to be emphasized, so I've redone it. So I apologize if you looked at the other one. If not, lucky you. Let's just get on with it. Okay, so let's talk about projectile motion. What happens when we have an object that's in free fall, but is being projected both horizontally and vertically simultaneously? So when an object is in free fall, so it has both a horizontal and a vertical component of motion. That we talked about how these things are independent of each other. And what we have to remember is, it is the vertical component that's going to be subjected to gravitational acceleration, but the horizontal is not. So before we've just looked at things going off a table, but now we're saying, what if I shoot an arrow up in the air? Well, it has a horizontal component of velocity that's going to be unchanged as time goes by throughout its arc, but its vertical component will start large and get smaller because its velocity vector is pointing up and the gravitational vector is pointing down. It will eventually reach a vertical velocity of zero, but it still has horizontal velocity, and it will begin to increase its vertical velocity in the negative direction. So these are happening simultaneously, but keep in mind it's the vertical component that's subjected to gravitational acceleration, not the horizontal component. So let's just try this. So if I launch an object, say at 30 meters per second upward velocity and 20 meters per second horizontal velocity, I want to draw some motion graphs of the different components of motion. So remember, it starts off, it has 20 meters per second horizontal, 30 meters per second initial at launch vertical velocity. So what happened is 20 would stay constant all the way across, but the 30 would go down at 10 meters per second squared. So that means every second it's going to lose 10 meters per second of velocity. It starts at 30, a second later it's 20, then it's 10, then it's 0, then it's negative 10, negative 20, negative 30, right? So, A equals delta V over delta T. So let's just see what we get here. So if I was going to do a vertical velocity versus time graph, I have to remember that it starts off with a large 30 meter per second, positive 30 meter per second initial velocity, and that over time that will decrease at the rate g, right? Negative 10 meters per second squared. So it would look something like this. We've seen this many times. But what about the horizontal velocity? Well, the horizontal velocity should look like this. It's constant. It never changes. It was 20 the whole time until it hit the ground. If I did vertical acceleration, well, in the vertical direction, we know that the acceleration is going to be negative 10 g. In the horizontal direction, there isn't going to be any acceleration at all. We assume that there's no frictional, noticeable frictional loss of speed. So we say, the acceleration is not going to be there in the horizontal direction. For the vertical position, so it starts off going very quickly upwards, so it has a steep slope, and over time that slope gets closer and closer to zero. And in fact, if it was projected upward at this velocity, it would reach about this height here, and then we'll come back down. And remember, smiles are positive and frowns are negative, so we see this negative acceleration, which we would associate with gravitational acceleration working on an object that has an initial positive velocity, a positive slope. If I do this for the horizontal, though, what I should notice is that and it should say horizontal here, sorry, it doesn't, that it's just going to move horizontally at a constant rate the whole time. And that rate is going to be 20 meters per second. So every second is going to go another 20 meters in the horizontal direction. Now, sometimes, though, we want to talk about the speed of the object. Now, remember, speed is a scalar quantity. It doesn't have a vector component to it, but we have to keep in mind that the speed of that projectile is changing over time. Although the horizontal velocity stays constant, the vertical velocity is constantly changing. So to find the speed, we'd simply use Pythagorean theorem. We'd say, well, I know that the horizontal is 20, the vertical is 30, so the resultant vector would be, I'm doing tip to tail, I would get 20 squared plus 30 squared, take the square root, I get 36 meters per second would be the speed of this. And basically, I'm just taking Pythagorean theorem, and it makes sense that it's a little bit more than 30. If I wanted to find the angle, and this is something we're going to have to do some. So if I want to find the angle, I have to remember SOHCAHTOA. All right, so the TOA part means tangent, opposite, over, adjacent. So if I want to find this angle, and often we do this with a launch angle. If I want to find this angle, I know the initial vertical velocity is 30 and the horizontal is 20. So I say this theta is the tangent of this value here is going to be equal to 30 over 20. So tan theta equals 30 over 20. If I want to know what the value of this is, then I have to take the inverse tangent to find what theta is, right? So the inverse tangent of 30 over 20 gives me 56 degrees. And that makes sense that it should be more than, well, I'm getting a little ahead of myself. We know it's a little bit more than 45 because this value is larger than that one. If they were both the same, it would be 45, but we'll get to that in just a minute. Well, look at this graph here. So if I did a graph of its speed over time, what I'd have is if I do Pythagorean theorem on each of these, here's what I would get. It starts off at 36, and then it gets less and less, but it's going to have a minima at 20. It's never going to go slower than 20. It doesn't go to zero, right? At the apex, and College Board likes to ask this question. At the apex, it's still got horizontal velocity, so it still has a speed. The smallest speed it will ever have is going to be 20. Now remember, speed is scalar, so there's no negatives associated with it. Okay, now to the real heart and soul of this, okay, and that is that the amount of time an object is in the air is going to be determined by the vertical components that it has. Okay, so that means it's going to be the vertical component of velocity. Like whatever its velocity is, the vertical component is going to decide how long it gets to be in the air. The vertical displacement, how far it has to fall, like the car going off a cliff kind of problems, and of course gravitational acceleration. If you're on a planet where g is smaller, it's going to be in the air longer, and if g is greater, it's going to be in the air less time. Horizontal displacement is going to be entirely determined by how fast the object is traveling horizontally and how long it gets to stay in the air. And how long it gets to stay in the air is determined by these vertical values. So these vertical values are going to be really crucial in solving these projectile motion problems. We usually start with those to try to figure out the amount of time, and then we apply it to the horizontal um, component of velocity. So let's try this one here. I got a soccer ball leaves the ground with a vertical component of velocity of 25 meters per second, uh, and it lands 60 meters away. What was the horizontal component of the ball's velocity? Well, here's a trick. Okay, so I know that this ball is going up at 25 meters per second, and I wonder how long it's in the air. So I can say as well, here's a good way to do it, is I'm going to say, if I want to know how far it goes this way, that would be equal to velocity equals delta x over t. So v times t is going to give me delta x. We've done this so many times now. But for the time, I like to call these up and down problems. I would use this to figure out how long it goes up for. So it's accelerating at g, negative 10 meters per second squared. The final velocity on the way up is 0. I know that. And the velocity that it left with was 25. So if I do this, I can say, well, then what I've got is 25 divided by 10 is going to be 2.5. So yeah, no, it goes up in the air for 2.5 seconds, but then it's got to come back down for another 2.5 seconds. So actually, the time is going to be 2 times that. So we have to remember when we're doing these problems, you have to take the time it goes up for and double it because it has to come back down. All right. Now that I know it's in the air for 5 seconds, then I can say, well, uh, uh, if you go 60 meters in 5 seconds, that means you've been traveling at 12 meters per second. All right. So the trick here is using that vertical component of velocity to figure out the time the object is in the air. Now, sometimes we're going to have problems. Frequently, we're going to have problems. College Board loves to give you these problems where they give you the launch velocity and launch angle. And then it's up to you to say, well, if I'm going to solve this problem, I got to break this up into its horizontal and vertical components. I can't solve these kinematics problems otherwise. So the trick is, if you just remember SOHCAHTOA, so this is basically the hypotenuse. So opposite. So here's our angle is 60 degrees. The opposite side, that's sine, right? So that's the sine opposite, right? And so here the opposite is going to be the 50 times the sine of 60 is going to give me the vertical component, and the adjacent was that's the right? So that's going to be then 50 meters per second times the cosine of the angle. So just remember, if you want to find the vertical component, it's the launch speed times the sine of the angle. And if you want to find the horizontal, it's the launch speed times the cosine of the angle. And this comes up a lot. So you just need to memorize this. I put some Quizlets into Schoology so that you would have ability to just go through and memorize this one. You really need to get this one memorized. All right, let's try another one here. Okay, so I have an arrow fired upward at 60 meters per second, angle of 30 degrees. How far away does it land? Okay, assume it lands at the same height that it was launched from, because that way it just simplifies the problem quite a bit. All right, so here you go. All right, I first find the vertical component of velocity because that's going to determine how long it's in the air. So to find the vertical, remember, I'm going to take the launch velocity 60 times the sine of the angle, which was 30. So when I do that, I get 30 meters per second because the sine of 30 is 0.5. So that gives me 30 meters per second. Now, based on that, I know it's going to go up for 3 seconds and it's going to come down for 3 seconds. So it's going to be in the air for 6 seconds. Now, the horizontal component is going to be 60 times the cosine of 30, which is this. Now, by the way, these please keep in mind, these two do not have to add up to 60. The square of this plus the square of this, take the square root, that's going to be 60, but these two don't equal each other, okay? These don't add up to 60. Now, so this is what I'm going to use to figure out the horizontal distance. This is what I'm going to use to find the time because it's the vertical values that determine the time. So again, if I want to solve this here for the horizontal distance, I've got VT. I know V, but I don't know T. So I'm going to use this one here to find T. So I'm going to say, well, I know that the final velocity on the way up was 0. The initial vertical component was 30. So therefore, it went up for 3 seconds. It had to come back down. That's 6 seconds. And then I say, well, I'm going to put 6 here. I'm going to put 51.96 here. And now I squeeze it up here. Don't ask me why. It's going to go 311.76 meters. I think that's all I've got for you here. Oh, no, no, it's not. Duh, I have to do this one too. Okay, it's important to keep this in mind that uh, that if I take an object and I shoot it at a low angle, it has a very high horizontal velocity, but it doesn't get to stay in the air very long. And as I tip it more and more upwards, from 10 degrees, 20 degrees, 30 degrees, what's happening is it's in the air longer, but it's got less horizontal velocity. So, you're trading one for the other. And it turns out, I'm sure you won't be surprised to realize this, that at 45 degrees, it gets the greatest. So if I shoot at 15 degrees, I'm shooting at 99 meters per second. Here's what I get. It lands here. If I shoot at 30 degrees, it's in the air longer, but I traded some of the horizontal velocity for some vertical velocity. It went further. But it turns out if I shoot it at 45, that's going to give me the maximum distance. If I aim at more than 45, it's in the air for more time, but it's going slower, so it doesn't go as far. And if I shoot, the higher and higher I shoot it, the longer and longer it's in the air, but the less horizontal distance it has, so the shorter distance it goes. Now, a fascinating thing here is this: if you notice, for every distance or every horizontal distance it can go, there are going to be two angles that will put it there. All right. So there's angle theta. So that say theta is 15 degrees, and there's 90 minus theta. So 90 minus 15, that's 75 degrees. So 15 and 75 will both put it in the exact same spot, right? If I shoot it at 60 degrees, well, let's suppose I shoot at 30 degrees, it lands here. 90 minus 30 is 60. If I shoot at 60, it goes the same distance. So there's two distances, there are two angles that'll put it the same distance, as long as we're landing on the same level. If we're not landing on the same level, it's a little bit off. I think once they've asked a question about this in College Board, which is just that, well, if I think about these parabolas, it's possible to have it go further horizontally if it's falling a greater distance. So because the having that large horizontal distance, I get to fall more time because I'm here. So they might ask a question about that. So 45 being the angle that's the furthest is only true when it's going from like from the same launch point to the same end point. All right, last one here. Okay, so I have a ball leaves the ground at speed s. Angle theta, it's in the air for time t, lands horizontal distance delta x away. If it left the ground at the same angle but at a speed 2s, how far away would it land? Well, let's think about this. The vertical component would double. So if I double s, the vertical component doubles, and so does the horizontal component, right? If we make this twice as much, this one is twice as much, this one's twice as much. So since it's the vertical component doubled, it's going to be air twice as long. However, its horizontal one doubled, so it's going twice as fast horizontally. So therefore, it's going to go distance 4h away. Well, I moved my faces in the way, so it's going to go 4x away. All right, thanks for watching this. It's a little bit longer than I meant for it to be, but it's better than what I had before. So if you watched someone before, sorry about that. This one's better. Bye, guys. Have a good chew sock.